Good morning, everyone. Today we'll be discussing about Hadamard transform. Now, in the Hadamard transform, as we have already discussed previously about the DCT, discrete cosine transform, and then discrete sine transform, the formula for the forward and the inverse transforms, they remains the same. Just the matrix what we calculate it changes. Okay. So the rest of the method it remains the same. Okay. Now it is one of the most easiest transform where we can calculate the transformation matrix very quickly. So the formula is that if you are using a 2-point this thing 2-point Hadamard transform matrix, so we can write it down as 2 to the power n 2 to the 1. If you are calculating the Hadamard transform for a 4-point Hadamard transform, then we can write it down as 2 to the power 2, and then subsequently for 8-point we can write it down as 2 to the power 3. Okay, so this n values why I have calculated, because in Hadamard transform what we get is that h equals to 1 by under root of 2 to the power n is calculated depending upon whether we are calculating for 2-point, 4-point or 8-point Hadamard transform. Okay, so for the 2-point, let us first calculate the Hadamard transform for a 2-point Hadamard transformation matrix. So the n becomes 1 by under root of 2. Now what about this matrix? So we have seen that this will become 1 by under root of 2. And what about this matrix? So this matrix is that we are having, we have to divide the matrix of the transformation matrix into 4 parts. And in the first one, in the 2 by 2 matrix, our first point is 1. Then other 2 quadrants, so say this is the first quadrant, this is the second quadrant, this is the first quadrant, this is the second one, this is the third one, and this is the fourth one. Okay, so the values of the first quadrant is being replicated in second quadrant and third quadrant, whereas in the fourth quadrant we get a negative of the value of the first quadrant, so minus of 1. Okay, so the Hadamard transform matrix for a 2 by 2 system comes out to be 1 by root 2 multiplied by 1 1 1 minus 1. Now this value is again used for the calculation of the higher order matrix. Okay, so in this case it is one of the transforms where the lower order transforms transformation matrices are used for the calculation of the higher order transformation matrix. Now let us come to the 4-point Hadamard transform. So again let us write down, let us break this matrix into 4 quadrants. So this is how I have broken down. Now in the 4-point Hadamard transform matrix, the first quadrant will get the value of the 2-point Hadamard transform matrix, that is 1 1 1 and minus 1. So if you see over here, I have written 1 1 1 minus 1. So in our previous in 2-point system, I have told that the second quadrant and the third quadrant, they get the value which has been put into the first quadrant. So if you see, we are getting the same value 1 1 1 minus 1 again in the third quadrant, 1 1 1 minus 1, and in the fourth quadrant we'll be getting a value which is a multiplicative of the values of the multiplicative of minus 1 of the values of the first quadrant. So we get minus 1 minus 1 minus 1 and 1. Okay, now for the calculation of the 8-point Hadamard transform, so let me erase this one. Now for the calculation of the 8-point Hadamard transform, again let me draw the quadrants. So this is one of the quadrants. So again, so I have broken down the quadrants in this fashion. Now if you see over here, this first quadrant, it is getting the value of the 4-point Hadamard transform matrix. Sorry, in the 4-point Hadamard transform matrix, I forgot to tell you the coefficient this thing. So this coefficient is 1 by under root of 2 whole square, which comes out to be 1 by 2. So if you see, this comes over here. Now in the 8-point this coefficient is 1 by under root of 2 to the power 3, which comes out to be 1 by 2 root 2. So this 1 by 2 root 2 it has come, and then in the matrix we get the first 4-point Hadamard transform matrix and we put it over here and we get these values. Then in the second quadrant, what will happen? This same value it will be put over here. Third quadrant also it will get the same values. Now in the fourth quadrant it will be the multiplication of the values with -1 of the first quadrant. So see, -1, -1, -1, -1, -1, -1, 1, -1, 1, -1, 1, -1, 1, 1, -1, 1, 1, -1. So this is how we calculate the 8-point Hadamard transform matrix. Okay. Now coming to the example. So this is the image which is filled with 1 4x4 image. The pixels are being filled with 1, and this is the Hadamard transform matrix, and here we get the V intermediate, which is the intermediate of the transformed image. And again, when this matrix is being multiplied with Hadamard transform transpose, we get this image. Now if you look in this image, just like in the DCT image, we have got 4 in the 0, 0 pixel, and all other values are zeros. So there is a high data compression over here if the image is highly correlated, and when we perform the inverse transform, we get back to the original image. Okay. Similarly, in this example also, we get the same thing. If you look into the transform domain image, it is having a very significant image in the 0, 0 pixel, and all other values are not very significant. Okay. The main consideration which we want to see over here is that it is only addition and subtraction which is needed for the implementation of the transform. Okay. Because of this reason, Hadamard transform is a fast transform, and it provides us very good energy compaction for highly correlated data. Okay. So I hope I have been able to make you understand what is happening over here, and you should be able to calculate both the transformation matrix and do the numericals. Okay. Thank you very much for your kind attention.